to this series of films about fluid flow measurements, and this first film will be about the fluid flow theory. When we talk about fluid flow, it's a part of the fluid dynamics. Fluid dynamics is the science of fluids in motion, so when they're not stationary. And it can be divided into two subgroups, aerodynamics and hydrodynamics. Aerodynamics, every gas and vapor that may flow, and hydrodynamics, liquids that flow. When we talk about the fluid flow, we have two kinds of measurements. The volumetric flow rate is the cubic meters per second. So it's the volume per second. And the flow rate is defined as Q, and it's the area multiplied by the average velocity. In a pipe, we have a velocity profile like that, which means that it flows faster in the center of the pipe and slower at the ends, at the walls. While the average velocity is the average of the flow you have there. So the flow rate is where we use the average overall. What would end up in the tank where this pipe ends. Sometimes you have a tilted area, then you need to introduce a cos angle element, but for most practical purposes the area where we measure the flow rate is perpendicular to the flow. Also in this case the area is the total pipe section, and that is for most cases the most convenient thing to measure, because we are really interested in what is flowing out of the pipe at the other end. But if we want to analyze the flow rate at different sections of this pipe, you can imagine that we have different areas here, and we measure different flow rates at these 3 points. So that is volumetric, the volume units per second. While the mass flow rate is named as m dot, and it also includes the density rho, the fluid density. Elsewhere it's the same with the area and the velocity. The unit is kilograms per second, and if you see here, the area is meters squared, density kilograms per cubic meters, and velocity meters per second. So if we combine all those three, we end up with kilograms per second. Also, it's very much as the volumetric flow rate. The only difference is we now introduce the density. So it's the volumetric flow multiplied by the density. The continuity of fluids. When we have a section of a pipe that narrows like the one in the figure here, the flow rate here, the cubic meters per second, or the liters per second if you like, must be the same here as here. You cannot have more fluid flowing here than here, for example, so the flow rate is the same at the 2 points there. So the area multiplied by the velocity equals the area multiplied by the velocity on the other side, and the same goes with mass flow. Therefore, if the area goes down like here, the velocity must go up. So the flow rate is the flow velocity is faster in this section, while the flow velocity is slower in this section. Bernoulli he took this one step further, and he found that the energy must be conserved. So the energy is constant throughout the pipe, unless you have effects like heating, etc., that the fluid heats the pipe, but that also is of course kind of energy, but Else, if you don't take the heat into account, you will have this relation here. What we really have is that the kinetic energy, which is associated with velocity, and the potential energy, which is associated with elevation and pressure, the sum of the two must be equal everywhere in the pipe. So here we have high velocity, which means high kinetic energy. Here we have low velocity, low kinetic energy. So here the potential energy must be low, and here the potential energy must be high. In most practical cases, we don't want that elevation element, so you can imagine here a pipe like this, where the elevation is the same all over the section, but the area differs. Here we have a high area, which means that we have a low velocity, compared to this end, where we have the high velocity. If we have a low velocity at the thick end, we also have a low kinetic energy, while here we have a high kinetic energy. If we have a low kinetic energy, we get a high potential energy, while in this end we have a low potential energy. High potential energy means that we have a high pressure, because the pressure is associated with the potential energy, and low pressure here. So in this pipe, when the fluid runs, we have high pressure here, and we have low pressure here. For many people that seems quite unnatural. Many people think that you will have higher pressure here, but that is not true actually. And you can imagine if you increase the fluid flow very much to the point where the fluid makes the wall of the pipe crack or burst. Do you think it would burst here or here? You can, for example, imagine if you have something like this. This is a bicycle pump with a piston, and you press the piston so much that the air escaping from this end of the bicycle pump, well, you press the piston so much that it bursts somewhere. Do you think it will burst here or here? Of course it will burst there, and that is due to the high power at the thick end.